Record again. Okay. So that's how our memory system works. We remember stuff from the long term. We remember most of the short-term stuff. Well, you might say that if you remember everything from the long term, then you need lots of memory, but we forget things from time to time, and there should be some mechanism of forgetting things. So we learn how to learn new stuff, and we learn how to forget stuff. That's how our brain works, okay? We don't remember everything. We learn to remember only the important stuff, but how do I learn how to forget stuff, right? That's the important thing. So these long short-term memory networks, they have a small network in it that learns how to learn new stuff or when to learn new stuff. The second sub-network learns how to forget some stuff. Some of the things are not important. I should forget them. And there is another network that says that if I know this, what should I output? That's another one. And the last one is, how do I combine the new learned stuff with the old learned stuff? Okay, so it's a combination of 4 different networks. The combination of networks learns new stuff, forgets old stuff, and tries to remember the important old stuff. Okay, that's called long short-term memory, and this is how it is. Okay, this is forget gate. Forget gate has its own weights, WF. Okay, those are the weights of what I am going to forget from the hidden state. Remember, this is our H is hidden state. Input gate says that controls what parts of the new cell content are written to the cell. So from the input, what I am going to input, what I am going to learn. Output gate is what I am going to output at this state. Okay, this is forget gate, input gate, and output gate. 3 different networks. Okay, and then I have the new cell content. See, these are sigmas. Okay, so the sigmas are, remember, between 0 and 1. Remember the sigmoid function. It produces something, whatever your input is. Okay, this produces a vector, this produces a vector, and this produces a vector. So if you put them together, it produces a vector. The sigma function is going to produce, for each vector element, a number between 0 and 1. Okay, now let's look at this one. Hyperbolic tangent is going to produce something between -1 to +1. Okay, this is between 0 and 1. 0 and 1 is 0 and 1. 0 means that forget that one. Okay, 1 means keep it. So you either forget it or keep it. Input is, it is either input this one, this input, or don't input it. Okay, ignore this part of the input or don't ignore it. Output is output something related to this part or output something that is not related. Okay, completely ignore that part of the output. Okay, so forget input and output gates. So let's look at this new stuff, the cell state. Okay, new cell content. Okay, what does it do? It says that get the internal state of previous case, okay, multiply it with the WC, okay, new cell content, and get the input of xt, my current input, multiply it with this UC, okay, new set of states, and bias. This one is going to produce something between -1 to +1. So that means what? Whatever the new input is, whatever I had known before, okay, calculate something between -1 to +1 so that I can I can produce a 0. If it is 0, then I ignore that one. I can produce -1. If it is -1, then I am kind of reversing whatever I know. +1, keep it as it is. And this is the cell state. What it does? Get the previous cell state. Forget you want to forget. Okay, this is FTC, this is FC. Get your previous cell state. Forget whatever you want to forget, okay, you like to forget or you calculated to forget, and add current, okay, whatever the current state is, okay, learn whatever needs to be learned and put them together, and that's going to be your new new cell state. And this is going to be your hidden state of the next case, okay? So hidden state of the next case is going to be get the tangent, hyperbolic tangent of the CT, again, -1 to +1, and multiply it with whatever needs to be outputted, and that will be your hidden state for the next one. So it looks like, so it is a bunch of new networks coming together. So how does this handle the, okay, I know what to do. I mean, I know what it's trying to do. Trying to learn forgettable things, trying to learn inputable things, trying to learn the outputable things. But how does this prevent the vanishing gradient problem? For that, we are going to look at this diagram, classical thing. Okay, this diagram, see this is HT, our hidden state. Okay, our hidden state, and our hidden state is, I have this cell, and this cell. This is for t-1, t and t+1. Okay, there is a line that continues in our hidden state, and there is a line that continues on our cell state. Okay, and these are our inputs, these are the outputs. When I write my loss function, okay, my loss is related to my input using one of these paths, right? Either there or there or there. If you look at this blue line will not get affected from any of these networks other than one network. It will not get affected from any of these, okay? So when you try to relate this one with this one, you will go through only one set of weights. That means what? When you calculate the backpropagation direction, when you calculate your gradient direction, you will take only one derivative across these gates. Okay? You won't be visiting any of these if you follow this line. That's what makes this long short-term memory very attractive in terms of handling the vanishing gradient problem. Okay? Again, the main idea is, okay, learn how to learn new stuff, okay, this is how to learn new stuff, right? This is input gate, right? Is this input? No, this is forget gate. See what it does? Learn what to forget and forget that much. So this one producing is something between 0 and 1. If it produces 0 for that n vector of n length, it's going to produce them it's going to forget them by multiplying it. If this one produces all 0, you are cutting all of your ties with the past, right? I forget everything. But if you are producing half zeros and half ones, you are forgetting some stuff, some unrelated stuff. You are keeping some of them, right? So this is our forget gate. This is our input gate. Input gate learns some stuff, okay? This one say that I am going to learn this part and this part and this part. And this one says that I am going to produce some important stuff between -1 and +1, this one, and multiply it with this 0 and what is going to be learned. And I am adding that information to my internal state. And this is about output stuff, whatever I am going to output, okay? So the part that kind of eliminates the vanishing gradient is this line here. Okay, that line can go as long as possible without going through any gates, any of these gates. And if you are doing the backpropagation, your backpropagation derivatives will go at most one gate set, and that will handle the most of the vanishing gradient problems. Okay, so I guess, oh, okay, so maybe I should have done it this way. This is the forget gate, this is the input gate, compute the new cell content, compute the output gate. See, one weight set here, one weight set there, weight set and weight set. Okay, so 4 new weight sets. Previously we had only what? Previously we had only which one? No. Well, kind of, but this one is more general. You guys are not listening? Did you get the answer? So this one is the one that we had previously, and we didn't have this line. Okay, we have to run it through this gate all the time. But you might say that if I combine these two, this kind of correspond to whatever we had. Definitely we didn't have the input gate and the forget gate. And you might say that the output gate is combined with this compute new cell. I mean, our cell content was our hidden state, and that was it. Okay, this is LSTM. Yeah.
If we have time, could you please re-explain that picture, because I'm
Which one?
kind of confused. This one, yes.
You like me to explain each of these boxes?
No, not each of them, but in general. For example, xt is the input, right? It is above.
This was input, yeah. And let's look at this one. This is concatenation. What is concatenation? If my input is 100 dimensional, if my ht1 is 100 dimensional vectors, if I put them together, this line is now 200 dimensional. Okay, that's one thing. And this is a pointwise operation. It means that multiply. So multiply this 100 dimensional binary vector. Well, it's not binary, but the values are between 0 and 1. With this 100 dimensional vector, is not dot product, it is pointwise operation. Okay, so you have this vector, let's say 100 dimensional vector, 0.7, 5.1, minus 2.1, and etc., 100 dimensional. Now I have 0.0, 0.1, 1.0, etc. If I do this multiplication, I will get our new hidden state. Okay, so the effect of this one is I forgot some of my cell content, right? Previous cell content. Yeah. So what am I forgetting? Maybe I am forgetting the object of the current word, right? Maybe I am forgetting whatever I had inputted from the previous sentence. Let's say our current input is this dot, right? Dot is a word, right? If I get this dot, that means that maybe I should forget the grammatical structure of the previous sentence altogether, because I am not going to use it. But this one doesn't mean that it should produce all zeros here, because I need to remember my co-reference. Remember the tickets thing? I should keep remembering the tickets thing, okay? But not the grammatical structure of it. Or maybe I should not remember the verb subject agreement, right? Because the sentence is all done. So this is the input gate. It learns this kind of stuff. Of course, it doesn't think like we are thinking, right? Because it doesn't know about the language. It doesn't know about the grammar. But it learns by looking at this, okay? By looking at this output, right? If my input is this, my output should be this one. And if my input is this, my output at this phase should be this one. Okay? I am minimizing still that one. So my input, my forget gate should be changed in a way that my loss for all of these outputs is minimum. Okay? That's my forget. This is my input. What should I learn? Okay, how much should I learn? This one tells how much should I learn. This one tells what should you learn. Okay, and there is a reason this is a sigma, this is a 10H. This one is again between 0 and 1. This one can say that don't learn this much. It is 0. Okay, this one is going to tell you what you should learn. It is between -1 to +1 because whatever the output is going to be added to my cell state. Sometimes it can diminish some of the effects, sometimes it's going to increase it. Okay, this one makes the decision how much of it should I learn. And this one says that what should I output from my current hidden state? What should I output? Okay, again, this one is, let's say, 100 dimensional, right? 100 dimensional is going to come here. Okay, I am going to put this there is no network here, right? This one, these are all functions. Networks are here. Okay, weight set, and weight set. Okay, whatever my cell state is, I am going to run a output network. From this output network, okay, this will be multiplied by zeros and ones again. What I am going to output will depend on this 10H, which will produce numbers between -1 to +1. Okay? So, did I answer your question? Or I just repeated whatever I told you before. If you have any questions on this. I am trying to achieve two things here, okay? One thing is, let's get this vanishing gradient problem, some solution. Let's produce some solution to this vanishing gradient problem. The second thing is that, how am I going to remember these long-term relations? Okay? I mean, if I try to keep all the things in my mind, then I need lots of memory. That's one thing. The other thing is, how am I going to find the related stuff out of this loss of memory? Okay, so the obvious answer is no. Don't keep everything in your mind. Forget things. Okay, but you should know what to forget. Okay, you should know what to forget. When somebody tells you, okay, when I meet new people, they tell me their names and they tell me their phone numbers too. I immediately forget their phone numbers, but I try to remember their names. But usually I am not that successful in both of them. I forget both of their names and the numbers, but I shouldn't forget their names, right? Usually, unfortunately, maybe I shouldn't say this on camera, but usually I forget the students' names. I try to get their faces first, because I don't know why I forget students' names, because, well, I am not going to see them next semester maybe. If I keep seeing them, okay, every week, then I remember their names. Maybe my network works that way, right? And after some tens of years of living on this world, I realized that I don't have enough memory to keep all the names on my head. So I tend to forget most of the names anyway. It is not in my head, right? There is some kind of a network running somewhere there. Forget this name, forget this name. Well, in fact, forget all the names. You don't have to remember any names anymore. Sometimes I feel it that way. So this is what I am trying to achieve here. The second thing is that, okay, if I am going to relate these two together, and I have this gradient descent approach for the optimization, then there should be a direct line of connection between this output and this input, and it will be over this blue line. Again, over the blue line there are no gates. there are no networks. Only these multiplication, addition operation. Okay? That's the main idea of LSTM.
So it also doesn't use this value on any network calculation or output calculation.
What value?
This value on blue line.
Blue line is not, oh, no. This is, no. See this one? This one goes like this. Right? So this one produces tan H. It is between -1 and +1, right? This one says that whatever you have produced before, I'm going to multiply them with between zeros and ones, right? That will be my output. Also, that will be my internal, my hidden cell state. Okay? So two things are going on. Two things are going on. By the way, when I say there is a direct line between this and this, right? And that direct line goes only one set of gates. That's not exactly true. This one is going on too, right? This one goes through, okay, sorry. This one goes through like this, and like this, and like this. So it goes through many gates if you are following the red line, but there is a shorter line, and your gradient will get affected from the shorter, more direct blue line. Okay? So that's what LSTM is all about. Okay, the LSTM architecture makes it easier for the RNN to preserve information over many time steps. If the forget gate is set to 1, remember forget gate can produce values between 0 and 1, and input gate is set to 0, then the information of that cell is preserved indefinitely. Okay? In contrast, it is harder for vanilla RNN to learn a recurrent weight matrix. Okay, let's get some break. I am getting a net phone. Efendim? Teşekkürler. Yaratıyorsunuz. Hangi dosyaları? Evet. Ha yok, ben bugün bakamadım. Ne zaman gönderdiniz onu? Ha yok, ben bakmadım ona henüz ya. Yarın, evet, biliyorum, evet. Başvuru mu var? Tamam, ben bu akşam bakıyorum. Hadi, diğer hocalar açamamışlar mı? Tamam, ben eğer bir problem çıkarsa sizi ararım ben, ama açabileceğini düşünüyorum ben. Teşekkürler. Güle güle.
Hocam, yarın haftalık toplantı sırasında benim sınavım var, fotoğrafçılık sınavı. Size rapor yazsam olur mu?
Çakışan dersi nasıl alıyorsun ki sen?
Fotoğrafçılık dersi salı günü de, yani o gün yaptı. Akşam üzeri salı günü.
Bir dakika, senin ne? Ha, finalde.
Evet.
Merhaba hocam. Hocam ben şey için aradım, bu bilişim komisyonu kurmuştuk yani. O güzel, geçen hafta toplandık, fena da değildi. Haftaya bir daha toplanacağız herhalde. Geri dönüşler falan güzeldi ama hocam sanırım bir dakika hocam, ben dışarı çıkayım şuradan, bir de asitlerimi alayım. Yok ya, ders değil ya.
Çok bir şey yapmadım aslında. Harbiden.
Okay, so how does the LSTM solve the vanishing gradients? Well, it doesn't solve it. It helps it, okay? It doesn't guarantee that there is no vanishing exploding gradient, but it provides an easy way for the model to learn long distance dependencies through fewer layers of networks. Okay, so what? Okay. At the beginning of the semester, I told you this. I'm going to teach you about the classical methods of doing NLP, like the parsing and the morphological analysis, and dynamic programming, and etc. And then I said that I will talk about the neural language modeling, neural networks for NLP, and etc. And like a few years ago, maybe 3 or 4 years ago, no, 3 years ago, LSTMs were the state of the art. Nowadays, LSTMs are dead. Okay, nobody uses them anymore. I mean, if for teaching purposes, for trying something fast, or for very small amount of data, we use LSTMs. But nowadays, it is all transformers. Okay. Transformers are not related to LSTMs or RNNs. In fact, remember, one of the problems with the RNNs is that they are difficult to train because they are not parallelizable. Transformers are just the opposite. They are very, very parallelizable, and they are doing some other stuff related to attention, and we are going to talk about it, okay? But RNNs or LSTMs, they were started, they started using in 2015 and etc. Okay, so this is an interesting number. Okay, so they made a search. Okay, they made a search in these years. It says that in 2016, summary report contains 44 RNNs. Okay, in 2018, report contains RNN 9 times and transformer 63 times, and in 2019, RNN is 7 and transformer is 105. Okay, so machine translation conference. Nowadays, nobody talks about RNNs or LSTMs. Okay, everything is about transformer. Today, I will talk about some machine translation, and we will talk about attention, which is the basic principle of transformers. And next week, I think I will talk about the whole transformer thing. Okay, so I guess we talked about this. Okay, yeah, well, this is not LSTM, but this is GRU, gated recurrent units. As I said before, this is simpler, gated recurrent unit. This is update gate and reset gate. Update is kind of input plus the output gate, and reset gate is forget gate. Okay, these are the same thing. So the number of gates for a gated recurrent unit is one less than the LSTMs. So this one is a simpler network structure, GRU, but the idea is the same: what to update and what to reset, what to update and what to forget. Okay, so again, it helps with respect to addressing the vanishing gradients. And if you don't have much data, GRU is the logical step to start using the LSTMs. Okay, rule of thumb is LSTM is good default choice, especially if your data has particular long dependencies. Switch to GRUs for speed and fewer parameters. Okay, good. So the other thing is this: I mean, vanishing or exploding gradient is just an RNN problem? No. What is deep learning? Deep learning is you have a neural network of many layers. Okay, I'm going to draw it here. Okay, if this is my input, there is a network layer, another network layer, another network layer, another network layer. Okay, In 2012, if you did 10 layers, you are deep, okay? This is the best deep learning network you can have, okay? The gradient descent algorithms that we used during those days were good enough to address 10 layers only. But people have realized that more layers means better generalization, better networks, better numbers altogether. But if you add more layers on top of it, okay, your performance gets worse and worse because of this vanishing gradient problem. I cannot push my gradient information back to the original, the first layers, okay? So vanishing gradient started becoming a problem. Then somebody invented this. They said that if I have a layer here and another layer here, why don't I have a skip connection, a direct connection between this layer and this layer? So I am skipping these two. The information still flows, but there is another free flow direct connection between the layers, and these are called skip connections. Okay? And these kind of networks, they are called residual networks or ResNet. Residual networks or ResNet. Okay? When ResNet introduced this idea in 2016, I don't remember, what was it? 2015. Okay? 2015. Okay, when they invented it, all of a sudden, our typical number of layers went from 2 to 20 to 100 and 150. And it was even possible to have more than 1,000 layers for some networks, okay? So that was the enabling technology. It was as simple as this, okay? So I just add this X value to the output value of this weight layer or the neural network layer. That was a skip connection, and we said that this definitely helps the vanishing gradient problem. And people later, they generalized this into this. Well, why not connect everybody to everybody? Okay, not just two, but this one to this one, this one to this one, this one to this one, and this one to this one. And these are called dense networks. And dense networks are better than, of course, residual networks. And it is 2017. And it is the same around the same time. Well, these are not NLP networks. These are mostly image processing networks. There is no time, there is no single dimensional data anywhere, okay? But in our application of the LSTMs, we are doing something same. When people came up with this idea, they were criticized with they were criticized in a way that their invention is not good, is not new. In 1997, RNN uses the same idea, or 1998 LSTM. By the way, LSTMs are old. They are older than the original deep learning methods. I think it is from 1990s or 2000s at least. They say that LSTMs are using the same idea, and etc. and etc. But usually, I mean, we understand that we came to the same conclusion from two different areas, from the LSTMs and from the residual networks or the dense networks. This kind of structure, skip connections, are good for the vanishing gradient problem. Okay. There is another one, famous one, highway networks. Highway networks are a little bit older than the dense nets or the residual networks. They are more general, but they don't work better than residual networks. Okay. Good. So we talked about those. So the conclusion is, though vanishing histodegrades are a general problem, RNNs are particularly unstable due to repeated multiplication by the same weight matrix. And people knew about this problem in 1994. This Bengio is one important figure in the deep learning world. Bengio and Hinton and LeCun, those three guys. I think they got the Turing medal for their contributions for the deep learning world. Okay, good. So, just to sum up, vanishing gradient problem. We talk about it. LSTMs and GRUs are effective tools to address the vanishing gradient problem. While we are solving the vanishing gradient problem with the LSTMs and GRUs, we are solving the long distance relations in natural language processing. So I think last week I talked about this a little bit. Bidirectional multi-layer RNNs. Let's kind of repeat them. Okay. So this is a network that takes a sentence. The movie was terribly exciting. Okay. The movie was terribly exciting. This is the sentence. I feed it through an RNN. Okay. I get all the internal states or the hidden states of all the steps one by one. I took it as an input to my sentence encoding network, and I output one thing, a positive or negative. So is this a positive review or negative review? But the thing is that my result is dependent on my order of taking the words in from the left to the right. So why am I using it in this direction? Why don't I use it the other direction? That's what the bidirectional RNNs do. Okay, two different networks. One is from forward. One is forward network. The other one is a backward network. I take their internal states or the hidden states for each time step. I put them together, and whatever they output, okay, I feed them to a network, and they will make a decision. These are called bidirectional RNNs. The other approaches other than the bidirectional RNNs, okay, forward RNN, backward RNN, these are the concatenated versions. So my current state is this one, HT. Okay, the other one is multi-layer RNNs. Why don't we feed the output of each time step to an upper layer RNN? So the input to this lower layer is the word itself. The second one is going to be the output of the first layer, second layer, and third layer. Usually 3 or 4 layers are enough for this kind of multi-layer RNNs. And the experiments show that this one works better. This one works better. Multi-layers RNNs, okay. So 2 to 4 layers is best for encoder RNNs, 4 layers is best for decoder RNNs, and we are going to talk about encoders and decoders in a few minutes. Okay. For the transfer-based networks, okay, 12 to 24 layers, we will see them next week. Okay. Good. So I guess that will be it about the RNNs and LSTMs, and now I'm going to look at this neural machine translation as I said, ultimate application of natural language processing is a machine translation, and we are going to see it in a few minutes. Any questions? Can you put your phone away? Yeah. Put your phone away. Put your phone away. Yeah. Don't put it away in front of the desk. That desk. No. The desk in front of you. You don't have any other phones, right?
No.
You don't? Okay. So what are you gonna do now? Listen to the lecture? What are you gonna do now? Listen to the lecture maybe? Okay, that would be good. Okay. So we talk about this fancy neural machine translation. Okay. So machine translation as a major use case of the natural language processing. We are going to look at this network structure, sequence to sequence. This is With NLP, we use this a lot, but it's a more general thing, sequence to sequence. And we are going to look at this idea of attention. Okay, let's start. Machine translation, of course, this. Given this French sentence, what is the corresponding English sentence? Man is born free, but everywhere he's in chains. I don't know what that means, but I trust this is the target. This is the source sentence. Okay. As soon as the computers were started being used in any world, okay, people started doing two things, okay. The first thing is, let's play chess, okay. In 1955, they started writing chess programs or the checkers programs or that kind of stuff. The second thing is that let's do translation from one language to another one. And in 1950s, they thought that machine translation is done in a few years, 1 or 2 years. We don't need any translators, it has to be done. So all you need to do is just map the Russian words to English words one by one by looking up in the dictionary. That's one thing. The other thing is that we know the grammar rules. Just play with the grammar rules and that will be enough. Okay? So the rule-based stuff, map all the dictionary stuff, and the rule-based grammar translation, that will be it. But it turns out that the problem was much more complicated than it was thought. And we couldn't get the level of translation in, I think, in 60 years, 65 years. Yeah. It took us 65 years to reach to the levels of machine translation that they thought that they're going to do it in 2 years, right? Okay. So machine translation is like the computational linguistics dream, and nowadays it is becoming more reality. Okay, so up to 1990s they were trying to do rule-based stuff. If this is the input, then I'm going to translate it this way. If this is the input, then I'm going to translate it this way. Then they realized that it is not going to happen. This is a too simplistic approach. In 1990s, they started using statistical machine translation, Engram-based stuff, maybe you can say, or something related to that. So, what is statistical machine translation? Given this French sentence X, what is the probability that I am producing this English sentence corresponding to that one? And run this argmax expression over all the possible, okay, just carefully listen to this sentence. Run this argmax expression over all the possible English sentences to make this probability maximum. How many possible English sentences are there? Infinitely many, right? So if you try to optimize it, in the proper way, there is no way you can do that, okay? This is too expensive. Calculating this is difficult. After you achieve this difficult thing, calculating this is impossible. So we are trying to achieve impossible times very difficult thing. Good luck, but people didn't give up. So they work on this for 20 years, more than 20 years. After 20 years, and I'm going to show you something, okay? So again, given this French sentence, what is the corresponding English sentence that makes this P possible? Of course, as always, when you see something, we always write this, right? Okay, we just use the Bayes rule to write it Py times given Y, the corresponding, okay, Y is the English sentence, given the English sentence corresponding French sentence, okay? So this is the translation model, this is the language model. I solved this problem before, right? Using statistical language modeling, I solved this problem. If somebody gives me an English sentence, I can assign a probability to it, right? The important thing is this one. translation probability. Okay, language model, we know it. This is the translation model. So this is called fluency. Whatever I am producing, remember I am producing Y. Whatever I am producing should be fluent in English. Okay, whenever you hear it, you say that it's grammatical, it sounds nice, and normal people can use this kind of a sentence. The other one is fidelity, okay? I can produce very nice English sentences, but they should have the same meaning with the French sentence. That's the translation model. So I'm going to ignore this part now. We know how to do that already. I'm going to look at this translational model now. Okay, so statistical machine translation, for that we need a large amount of parallel data. And in fact, we have this parallel data already in our hands. And I'm not talking about our ancient Egyptian and Greek literature, because if you add this up, this kind of parallel data is going to be 2 kilobytes or 4 kilobytes. That's not enough. We are talking about megabytes of data or billions of sentences, parallel sentences. And luckily, we have lots of data like that. For example, there are some journals, there are some magazines that are published in 2 different languages at the same time. Some Arabic language journals. Canadian Parliament, they always keep their proceedings both in French and in English, right? Because in Canada, the official language is both French and English. Maybe they don't have an official language, but they keep all of their parliament proceedings in French and English. So you have the parallel corpora in there. Very narrow context documents. They all talk about law and foreign policies and the money and the economy, etc. But still, we have those kind of parallel corpora available. So why not use them? Okay. So this is what we are going to do. We will do it we will break it into further analysis. We will say that given the English sentence, okay, what is the corresponding German sentence and the alignment mapping? Okay, this is the English sentence, this is the German sentence. Okay, they correspond to each other. Also, I will separate this sentence, these 2 sentences, into parts, and I will give an alignment matrix or alignment map between these 2. This one will map to this, this one will map to this, this, and this. It looks like English is a subject, verb, object language. I will fly to Canada. I guess German is kind of different. Morgen fliege is fly, is I, right? So it is verb, subject, object, right? Turkish is ben Kanada'ya uçacağım. It is subject, object, verb, right? Right? So, I mean, when you model it this way, it looks like any alignment function that can map between these simple parts of the sentence of different languages. And alignment can do it fine, and that seems logical. But we'll see that this is more complicated than that, okay? So for each sentence, I have to come up with an alignment like this, because I have to come up with an alignment like this for each sentence. That's one thing. Also, see, the alignment is not word by word, right? 2 words, 2 words, 2 words, 3 words. 1 word, 2 words, right? changes from language to language. So how am I gonna know how to make these sentence sub-sentences, right? That's the problem. That's the problem. By the way, these are some, this is nice. English and French, they look like each other. They are similar to each other. My alignment matrix is like this, diagonal. That means that these two sentences are very parallel to each other. Word by word correspondence between French and English, but it is not always the case. Well, there is a diagonal thing going on here, but as you see, one word will correspond to 3 words. Again, one word will correspond to 2 words here, and sometimes this can happen just the other way, and sometimes that's it. I mean, there is no diagonality happening here, right? So the alignment is complex. You cannot say that there is one alignment. You cannot say that there is one alignment function and it's going to handle everything. Alignment depends on the sentence itself. Okay, sentence pair itself. So learning that alignment along with the translation is something difficult, but at least we made these problems. They are 2 different problems, and I can work with the alignment part and I can work the translation part in separately. Okay, so alignments A are latent variables. They are hidden. They aren't explicitly specified in the data. I have the parallel corpora, but the alignment is not there. Either somebody is going to sit down and say that this part corresponds to this part and etc., or I am supposed to find it myself. Good. Okay. We talked about the alignment, and other thing is, how am I going to compute this argmax? It is too expensive. Okay. Maybe I can do this. Maybe I can say that after finding the alignment, translate each sentence part separately from each other, okay, independence assumption, and that will give us some translation results like this. And if I can do that, if I assume that, okay, each part is separate, this one, they are all separate, they are different from each other, okay, maybe I can use this Viterbi algorithm like this. Okay, remember the Viterbi algorithm? Independence assumption. Each word is translated, or each sentence part is translated differently. Once they are translated differently, how do I combine them together? Okay, how do I combine them together? So that means what? For a sentence part, I will make a decision at this phase, another decision, and I will write another equation, another formula to combine these together, and I will find the shortest path here. Okay, so I can use this decoding approach, decoding with dynamic programming, and that will somehow work. And if you remember, like a few years ago, if you remember it, if you type something to Google Translate, usually 30% of the time, it gave us very, very funny results back, right? We laugh at it, and most of the people, we didn't use Google Translate for something useful. We use it to get some ideas about the words, right? How I use that word in Turkish, how I use that word in English, and etc. So that was the result using all this kind of complicated processing, okay? So it is extremely complex, alignment and sub-sentence translation, putting them together, lots of feature engineering. You need to have lots of knowledge about Turkish and English and French and Arabic, etc. Lots of extra resources like tables of equivalent phrases, etc. Lots of human effort, and all of them, it looks like it turns out that we cannot achieve anything more than laughable machine translation. Then came the neural machine translation, And this picture is, where is my picture? I'm going to show you that picture, and I am going to show you that picture and take some break afterwards. Yeah. Okay. Phrase-based statistical machine translation and syntax-based statistical machine translation. And these are the blue scores. Of course, the higher the value, better the machine translation quality. Okay. It looks like this phrase-based statistical machine translation, well, it is going up the numbers, but very, very slowly. Okay. And the syntax-based statistical machine translation, okay, the blue arrow is going up, but it is slowly. In 2015, people started using neural machine translation. And in 2016, it was already better than 20 years of progress made by the statistical machine translation. And this is interesting. In 2014, first sequence-to-sequence paper published. Sequence-to-sequence machine translation is neural machine translation. Okay. In 2016, Google Translate switched from statistical machine translation to neural machine translation. In just 2 years, I think this is unprecedented. We did not see such a progress in just 2-3 years. Okay, in just 2-3 years, you are doing better than 30-40 years of machine translation literature, and whatever you are doing is nothing to do with what you have been doing. Okay, the only thing that we kept from the previous 30 years of machine translation literature is what?
Data.
What?
Data.
Well, data is there. I mean, even without, if we don't do the machine translation, English sentences and French sentences are there. But yeah.
Word vectors?
What?
Word vectors.
No, we didn't have the word vectors in statistical machine translation. The only thing that we kept is how to measure our success. Blue things. Okay, so because I had to do this, right? I had to compare it. So in 1990s, we had how to blue scores, this one. Okay, we know how to we kind of come up with a method of measuring our success, our performance, success criteria. We are still using that one. It's not a very good way of measuring it, but just to stay compatible with whatever we have been doing, we are doing this. Okay, so this is very interesting. Okay, SNT systems built by hundreds of engineers over many years, outperformed by neural machine translation systems trained by a handful of engineers in a few months, and those engineers, they don't know the target language. Okay, they don't know French, they don't know Turkish, they don't know Arabic. Okay, most of them they don't speak English very well either. So that's the world of the deep learning, right? So people started producing very good, nice results, incredible results, without understanding the data they are working on. I mean, the control people, the control theory, robotic theory, they are producing results that are much better than what they have been doing for the last 50 years, and they don't know what they are doing. In image processing, computer vision, they produce results, and they don't know what kind of things that they are working on. And in fact, remember the picture that I showed you? This one? These are very incredible results, these are, right? The convolutional network plus the RNNs or LSTMs, okay? The people who worked on this problem, they didn't know much about English, they didn't know much about image processing, but they are doing this, producing captions for the images. So that's the world of the machine learning or deep learning. And that means what? Just ignore what have been done for NLP or the image processing or computer vision for the last 30 years. No, that's something that we shouldn't do, of course. That's the knowledge. We should never forget about it, but we shouldn't ignore the reality of the real world too. If neural machine translation is doing better than what we have been doing for the last 30 years, then we should learn it, then we should apply it. Okay, any questions? If there are no questions, then let's take some break. When we come back, we'll talk about attention.
Hocam ben aslında şey soracaktım da yarın bu bitirme toplantının sırasında sınavım var da.
Ha, sen bitirmeden bahsediyorsun. Evet. Tamam, oldu, sen yaptıklarına bana bir şey yaptın.
Tamam hocam.
Bakarız. Ben de bu dersin finaliyle alakalı bir şey söyleyeyim. Ne diyorum ya? Bir dakika, bizim bitirme toplantımız akşam. Akşam mı yapıyorlar?
Akşam üzeri yapacağız.
8'de yapıyorlar.
5.30'da ama evine kadar yani 7 geçiyor. Sınav başlıyor da.
Bir şey olması gerekmiyor mu? Mesela tek tek yapıyorlar. Ben şeyde çalışmaya çalışıyorum ama burada çalışmaya çalışıyorum. Yıllar kadar çalışıyorum. Şey yaptım, şu oluşturmayı.